What is different here is twofold. One is we have a deep bench of expertise coming from NASA and JPL. These are people that have done this before time and time again. And by done this, I mean the aerospace process of packaging up satellites and observation centers and Mars landers and lunar orbiters. They've been doing this for decades, so this is not new territory for them. The other thing that stands us apart from the crowd is rather than fight the space environment for computing, we've rethought what it meant to be in orbit with a computer. So a lot of our competitors are looking at terrestrial computing solutions and retrofitting them for orbit, which means active cooling, which means repackaging existing servers. What we have done is we've rethought the way that computer should operate. We've looked at orbit and said, okay, this thing is going to be moving very fast. There's a lot of solar power. It's 4 degrees Kelvin. There's a certain amount of radiation at the level we're going to be at. Rather than fight those things, how do we make use of it all? And that's when we came up with the tile. So the tile is a flat object, not just because it looks cool, but because the components that power the computer are flat against the alloy that we're using to dissipate heat. So when you have a heat source and you're trying to radiate that heat out, you're going to get the biggest bang for the buck when you've got the largest delta between the heat being generated and the space that you're trying to radiate the heat into. So in orbit, when you've got CPUs and GPUs generating 120 degrees Celsius heat, radiation happens fairly quickly. So the biggest differentiator that Sophia has from our competition is the way the tiles are designed, the way we thought about computing, the way we thought about modularity of all of our computers, and the way that the operating system is going to handle the distribution of load and compute on those devices.